Chapter 7: The Constant Speed of Light and the Principle of Relativity. New Modern Translation 2025. Albert Einstein and Harry Yoon, Translator. Introduction. Chapter 7. The principle of relativity dates back to the time of Galileo, as stated earlier. But it's worth emphasizing that it was Einstein who realized its fundamental importance and full implications in physics. Newton, for example, didn't do much with the Galilean principle of relativity, other than using it to define the natural state of a body through his first law of motion, Chapter 5. Likewise, many physicists in the 18th and 19th centuries, especially those who were exploring the then newly discovered electromagnetic phenomena, cared little about the principle of relativity. In fact, there is no record that relativity was in the minds of the early pioneers in the field such as Coulomb, Ampere, and Gauss. Even when Ørsted and Faraday made revolutionary discoveries on the interactions between electricity and magnetism, they did not realize that their discoveries were incomplete, in view of one of the most fundamental principles in physics, albeit in hindsight. Maxwell himself didn't appear to have paid any attention to the principle of relativity. Only at the end of the 19th century did people start paying attention to this principle. As soon as people started studying the electrodynamics of the bodies in motion, they began to realize that Maxwell's electrodynamics and the principle of relativity were not in a complete harmony with each other. That was the beginning of the emergence of the new theory of special relativity. There were many telltale signs indicating the clear conflict between the laws of the motions of mechanical bodies and the new electrodynamics and optics. Einstein was particularly interested in a few of those, including the fact that the classical theory of electromagnetism appeared to be fundamentally in violation of the principle of relativity. For example, when we deal with the phenomenon of Faraday's induction, in which a magnet and an electrical conductor are in a relative motion to each other, we use two completely different explanations. In one situation where we view the magnet moving and the conductor at rest, we use one particular equation from the four Maxwell's equations to explain this phenomenon. On the other hand, in another situation where we view the magnet at rest and the conductor in motion, we rely on a different description. This clearly indicates that, at least in the way it is formulated, the classical electrodynamics of Maxwell is not consistent with the principle of relativity. Einstein's first paper on special relativity, on the electrodynamics of moving bodies, 1905, in fact primarily focuses on this riddle. In the previous chapter, Einstein explained how the velocities of two motions are added when we view the combined motion from a single frame of reference. At the end of the chapter, Einstein also mentioned that this simple and rather intuitive law of classical mechanics was not completely accurate in reality. In fact, this simple law is in conflict with other fundamental laws of nature, which is the topic of this chapter, Chapter 7, from the book, Einstein's Relativity, the Special Theory and the General Theory, New Modern Translation 2025. Chapter 7. The Constant Speed of Light and the Principle of Relativity. There is not a law in physics which is even simpler than the law which describes how light is propagating in empty space. For instance, every schoolchild knows, or at least they think they do, that light travels in a straight line at a speed 300,000 km per second. Furthermore, we know with great confidence and accuracy that this speed is the same for all colors. If this were not the case, then the last light of a fixed star for different colors would not be observed at the same time when it is being eclipsed by its dark neighbors. Through a similar consideration, based on the observations of binary stars, the Dutch astronomer Willem de Sitter also convincingly showed that the speed of light cannot depend on the velocity of the moving body which is emitting the light. Likewise, the assumption that the velocity of propagation of light depends on its direction in space is in itself implausible, which has no experimental support. Even if we ignore the abundant evidence, empirical or otherwise, we can just accept it as true that this simple law of the constant speed of light in a vacuum, denoted as c, is correct. This is clearly justified, as it is even believed by schoolchildren. And yet, inexplicably, this simple law seems to have driven some of the most intelligent theoretical physicists into the greatest intellectual difficulties. Let us now consider where and how these difficulties come from. First of all, like any other physical processes, we have to relate the process of the propagation of light to a specific rigid body of reference, or more or less equivalently, a frame of reference or a Cartesian system of coordinates. We once again choose our railroad embankment as an inertial frame, body of reference. For simplicity's sake, let us ignore the effect of air, by assuming that the air in the surrounding area has all been removed in some way. A beam of light is now sent along the railroad embankment, that is, parallel to the railroad track. According to the above law of light propagation in vacuum, the front tip of the beam of light then travels at the velocity c relative to the embankment. Let our train move on the track at a speed, v, with v greater than 0, in the same direction in which the beam of light propagates, say, to the east, but of course with a much slower speed than c. We now ask about the speed of propagation of the light beam relative to the train. As one can easily see, this is essentially the same situation as that of the previous chapter, Chapter 6. The man who is walking on the passenger car of the train plays the role of the traveling beam of light. Instead of the velocity, capital W, of the man relative to the embankment, the velocity of the light beam relative to the embankment is used here, whose magnitude is the speed of light c. The variable w in that example now refers to the expected velocity of the beam of light with respect to the train, corresponding to the velocity of the man walking forward on the railroad car with respect to the car. Hence, from the result of Chapter 6, the following applies. W equals c minus v. The speed of the propagation of the light beam relative to the train, w, thus comes out to be less than c, since v is greater than 0. However, this result violates the special principle of relativity that we presented in Chapter 5. According to the principle of relativity, the law of the propagation of light in empty space, like any other general law of nature, would have to be the same, regardless of whether we use the train as an inertial reference frame or we use instead the railroad embankment or the ground as a reference frame. But from the above simple consideration, this seems impossible. If every beam of light is propagated relative to the embankment with the same speed c, in a vacuum, then for this reason it would appear that the law of the propagation of light must be different with respect to the moving train relative to the embankment. This is obviously in a clear contradiction with the special principle of relativity. In view of this dilemma, we seem to have no other choice but to abandon either the principle of relativity or the simple law of the propagation of light in vacuum with constant speed c. The reader who has been carefully following our discussion so far from the beginning will certainly expect the special principle of relativity to be retained. This principle is so appealing to the intellectual mind, because of its naturalness and simplicity, that it seems almost absolutely incontrovertible. It would appear then that the law of the propagation of light in vacuum would have to be replaced by a more complicated law that is compatible with the principle of relativity. The recent development of theoretical physics in this area seems to indicate, however, that this path is not permissible either. The groundbreaking theoretical research of H.A. Lorentz on the electrodynamic and optical processes in relation to moving bodies showed that the experiences in these areas inevitably led to a theory of electromagnetic processes that established the law of light traveling at a constant speed in empty space as an inevitable consequence. Leading theoretical physicists were therefore more inclined to reject the principle of relativity, even though not a single empirical fact had been found which was possibly in a violation of this principle. This is where the theory of relativity came into play. A careful analysis of the physical concepts of time and space showed that, in reality, there was no actual incompatibility between the principle of relativity and the law of the propagation of light. Furthermore, according to this analysis, it was evident that a logically coherent theory would be, in fact, attainable by a systematic adherence to both of these laws. We call this new theory the special theory of relativity, in order to distinguish it from its further generalization, which is to be discussed later in the book. The fundamental ideas of this theory will be presented next in the following chapters. Translator's notes. In the previous chapter, Chapter 6, we derived Galileo's velocity addition formula in the context of classical mechanics. In this chapter, Einstein uses that formula with a propagating beam of light with respect to a moving train, and finds that the result is not consistent with the law of the propagation of light and the principle of relativity. A quick summary. The law of the propagation of light states that light travels in a straight path at the speed of c equals 300,000 kilometers per second in empty space. Let us consider the following scenario. A beam of light is sent along the railroad embankment, which propagates at speed c according to the law of the constant speed of light. Now, what would be the speed of this beam of light, w, relative to a train which is traveling at speed, v, in the same direction as the beam of light? This is essentially the same scenario that was discussed in the previous chapter. The beam of light corresponds to the man walking on the train in that scenario. Therefore, the following applies with respect to w with the substitutions, capital W with c, since the speed of light when viewed from the embankment should be c. W equals c minus v. The speed of the propagating beam of light relative to the train thus comes out to be less than c, since v is greater than 0. However, this result violates the special principle of relativity, according to which the law of the propagation of light, including the speed of light, would have to be the same in all inertial frames of reference. In view of this dilemma, we seem to have no other option but to abandon either the special principle of relativity or the simple law of the propagation of light in empty space. This is where the theory of relativity came into play. A careful analysis of the physical concepts of time and space showed that, in reality, there was no actual incompatibility between the principle of relativity and the law of the propagation of light with a constant speed. Furthermore, according to this analysis, it was evident that a logically coherent theory, which we now call the special theory of relativity, could be attained while adhering to both of these laws. The speed of light. The speed of light is one of the most accurately measured values in physics, or metrology. In fact, it is so accurate that we started using it to define the distance unit, meter, since 1983. The unit meter was invented as part of the metric system, and originally it was defined to be 1/40 million of the Earth's circumference going through both poles. A meter is now defined as the distance that a light ray travels in a certain fraction of a second, 1/299,792,458 of a second. It took a while, however, before we reached this current state of art. It's not clear when people started to realize that light propagated with a finite speed. This discovery is usually attributed to the astronomers at the time of Roemer, as we will discuss shortly. But it's more than likely that even ancient Greek philosophers supposed that the speed of light was finite, because many of them believed that infinity was not possible for various philosophical reasons. Light is one of the most important ingredients of the universe. Can you imagine a world without light? Light also plays such a fundamental role in our exploration of the world. Vision is arguably the most important sense for the human beings, as well as for many other species of animals. One can easily imagine how important the invention of the telescope was, in the early 17th century, in our understanding of the universe. Although Galileo's original astronomical telescope had only 9x magnification, modern astronomy relies on more advanced telescopes, whose effective resolution can be thousands of times higher than that of the naked eye. Virtually everything we know about the universe is based on the visual information, that is, based on the electromagnetic waves of various different wavelengths. Galileo's lantern experiment. Galileo was, in fact, one of the first scientists who attempted to measure the speed of light. There is little doubt at this point that he clearly believed or suspected that the speed of light was finite. Galileo and his assistant used the light of lanterns to signal to each other, which they presumed to travel at the speed of light. Imagine that Galileo and his assistant are located on two hilltops separated by 1 mile, with no obstruction between them. When one person, say Galileo, turns on one lantern from one hilltop, while turning on a stopwatch at the same time, the light propagates to the other person, his assistant. As soon as he sees the light of the lantern from the other side, he now turns on his lantern. Then, the light from this lantern travels back to Galileo. As soon as Galileo sees this light, he stops his stopwatch. Now he can calculate the speed of light by dividing the 2 miles for a round trip with the time taken by the light signals. Obviously, this is a very reasonable experiment. It wouldn't have taken Galileo to come up with this kind of idea. The only problem is that light travels way too fast for us sluggish humans. Light can cover 2 miles in roughly 10 microseconds. On the other hand, for comparison, the human reaction time is on the order of 100 milliseconds. That's a 4 orders of magnitude difference. Galileo's conclusion from this experiment? Inconclusive. Roemer's serendipity. So, if you were Galileo, how would you design an experiment to measure the speed of light, which you know travels extremely fast, with the benefit of hindsight? There is an interesting history behind the measurements of the speed of light. The first measurement happened really by accident. Since the time of Galileo, the gas giant Jupiter became one of the most favorite subjects of astronomers. In the late 17th century, based on the irregularities of the observed period of Jupiter's closest moon Io, an Italian astronomer Giovanni Cassini seemed to have been the first to draw an inference or at least speculate that the speed of light was finite. Then a Danish astronomer, Ole Roemer, who was working at the same observatory in France as Cassini, managed to estimate the speed of light using the same observation data, allegedly with the help of a Dutch physicist, Christian Huygens, based on the systematic variations of the apparent orbital periods of Io. Its period appeared to be shorter when Jupiter and the Earth were approaching each other, according to their relative positions with respect to the Sun. The reverse also held when they were receding from each other. This was due to the fact that it took a non-zero time for light to travel from Jupiter Io to the Earth, and to the fact that the distance between them was constantly changing because of their orbital motions around the Sun. This is a very interesting problem, which can be easily solved with no more than simple arithmetic, just as we did with regard to the velocity addition formula in the previous chapter. We will tackle a simplified version of this problem later in Appendix B. Bradley's aberration. A few decades later, an English astronomer, James Bradley, discovered again by serendipity what is now known as the stellar aberration. This phenomenon also has something to do with the fact that light propagates with a finite speed. Because of the Earth's motion around the Sun, the light of distant stars falls on the Earth at an angle, just like we feel a headwind when you move faster through the air. Of course, the effect is extremely small, but it is observable, as Bradley did in the early 18th century. Because the Earth moves in different directions throughout the year, we can detect this effect by observing slightly different apparent positions of various stars, with reference to the Sun. Based on this observation, one can also calculate the speed of light, assuming that we know the distances to those stars. We will leave it as an exercise, or something to think about, to the interested readers. Fizeau's tooth wheel. In the mid-19th century, over 200 years later since Galileo's lantern experiment, a French physicist, Hippolyte Fizeau, made another attempt to directly measure the speed of light. In a way, it was an improvement over Galileo's original experiment. Fizeau used a spinning wheel with hundreds of saw teeth, so that a beam of light could pass through, between two neighboring teeth, only when the wheel was spinning at a particular rotational frequency, or their multiples. Using this spinning wheel device, Fizeau was able to estimate the speed of light to be some 315,000 kilometers per second in 1849. We encourage the reader to think about this problem when they have some free time. How would you design an experiment, for example, solely based on the information that we just provided? How would you calculate the speed of light based on the speeds of the teeth that do or do not block the passage of light? It is not a difficult problem, and it will teach you how to do some basic calculations, which is an essential skill for any kind of physicists, including armchair physicists. We will revisit a bit different kind of Fizeau's experiment in Chapter 13. Foucault's rotating mirror. A few years later, after Fizeau's spinning wheel experiment, another French physicist, Léon Foucault, with the fame of Foucault's pendulum, had another go at measuring the speed of light. Foucault used a rotating mirror device instead, whose concept had been known for a few decades in the physics community, as a possible experimental tool to measure the speed of light. After over a decade of effort of refining the experiment, in 1862, Foucault was able to measure the speed of light at around 298,000 kilometers per second, which is remarkably close to the currently known value. Michelson's Interferometer. Now this is the golden standard of the modern times. The American physicist Albert Michelson, who we briefly mentioned previously in the context of the Michelson-Morley experiment, dedicated his entire life on metrology, the science of measurement. Michelson invented a new technology called interferometry in the late 19th century, which became the essential tool to define and measure units of distance, in particular. In essence, it works by splitting a beam of coherent light into two and combining them together after these two split beams have traveled through two different paths. Depending on the relative distance differences between these two paths, in terms of the light's wavelength, the combined light shows different interference patterns. Hence, in reverse, the distance difference can be inferred from the resulting interference pattern. Its precision is, in principle, only limited by the wavelength of the light used. In practice, however, this technique is so sensitive that external factors like mechanical vibrations on the apparatus affect its accuracy. Michelson and Morley used this newly invented interferometry technique in their second experiment in 1887, which we will discuss in some more detail in Chapter 16. Michelson's interferometer is now used in many scientific experiments, among other things, including gravitational wave detection. Michelson became the first American to receive a Nobel Prize in physics, largely thanks to his contribution to metrology, and not for the Michelson-Morley experiment, for which he is most well known. Michelson measured the speed of light over a span of a few decades, mostly using the techniques of Fizeau and Foucault, within the error range of only a few parts in a million. The best measurement of the speed of light now relies on Michelson's interferometer. What do we mean by constant in physics? Whether we like it or not, we will have to live with the common practice in physics, where the same words and phrases can mean different things, depending on the context. Conversely, we will likewise have to realize and accept the general tendency that we sometimes use multiple different words and phrases to refer to the same things. The word constant can mean many different things in physics. First, the usual meaning of constant in English as an adjective describes a characteristic of something that does not change or vary. The most common situation is when something does not change over time. That is, the value of interest is invariant with respect to time translation. For example, we used to, and still do, use the term, the Hubble constant, to denote the expansion rate of the universe, because we initially believed that this value did not change over time. Now that we have new evidences, and a slightly better understanding that the expansion rate has been actually changing since the Big Bang, some physicists prefer to use a newer term, the Hubble parameter. Even more fundamental is the situation where a certain value does not change over space. That is, it is location independent. But this is pretty much given. All known physical laws and fundamental constants in physics are all translationally invariant, as we have alluded a few times already. Hence, the word constant almost always implies location independence. Now, when we say a value is constant, it also implies, almost always, that the value is rotationally invariant. As stated, it is pretty much impossible to find fundamental physical laws or fundamental constants that are orientation dependent. When it comes to light, however, constant means a few more things. The constant speed of light. So what does it mean to say that the speed of light is constant? In the context of special relativity, it means the following. First, the speed of light is finite, as we emphasized earlier. This is almost implicit, since if the speed of light was infinite, we would not usually use the word constant. As with any other constant physical quantities, the speed of light is the same regardless of where you measure it or when you measure it. One thing worth repeating is that the speed of light is also the same in all directions. In addition, the speed of light is the same regardless of the relative speed of the source of the light with respect to an observer, e.g., an inertial frame of reference. Finally, in a way most importantly, all inertial observers measure the speed of light as the same. And just one more thing. The speed of light is the same regardless of its color. Speed of light for different colors. When Newton heard about Roemer's discovery, his first question to Roemer was whether the speed of light depended on its color, or wavelength, as we now know that they are closely related. Einstein also emphasizes this fact in the beginning of this chapter. We know with great confidence and accuracy that this speed is the same for all colors. Why do you think that it is important, or at least it was important to Newton and Einstein, that the light rays of different wavelengths, and hence different frequencies, propagate at the same speed? Addition of the speed of light. At the end of the previous chapter, Einstein mentions that the classical formula for adding velocities is not completely accurate. In this chapter, he provides one reason. That is, this formula is inconsistent with the law of the constant speed of light. For example, if you view a beam of light from the ground, it propagates at speed c relative to the ground. Then, the speed of light relative to a train moving in the same direction at speed, v, comes out to be c minus v, according to this velocity addition formula, which is inconsistent with the fact that the speed of light is the same in all inertial frames. Einstein compares this scenario with that of Chapter 6 as follows. The first row refers to the velocities in Chapter 6, and the second row shows the comparison. Clearly, we could have made the same argument starting from the train, since motion is always relative. That is to say, we can suppose first that the speed of light relative to the moving train is c, as it should be since the speed of light is constant. Now, if we use the classical velocity addition formula, the combined speed of light when viewed from the ground should be c plus v, which is bigger than c since v is greater than 0. This is again in violation of the law of the constant speed of light. Here's the comparison. We can even make the same argument with respect to two trains moving at different speeds, but in the same direction. There are really no differences, since we are always describing the motion of a body with respect to one other body. Einstein's riddle. This apparent conflict between the velocity addition formula in classical mechanics and the law of constant speed of light is rather intuitive, and it is easy to understand. While working on the special theory of relativity, however, Einstein seemed to have more focused on the fundamental way that Maxwell's electrodynamics was formulated. Figure, the asymmetry in classical electrodynamics. He used the word asymmetry in his first 1905 paper on special relativity to describe this situation. Here's the scenario. Let's suppose that we have an electrical coil and a magnet in the vicinity of each other, as shown in the figure above. In the first case, A, the magnet is moving, whereas in the second case, B, the coil is moving. Both of these two cases are described by Faraday's law of induction, and both result in an electrical current flowing in the coil. But the reason why there arises a current is completely different. These two cases are exactly the same according to the principle of relativity. And yet, in classical electrodynamics of Faraday and Maxwell, we use two completely different descriptions to refer to this same situation. This asymmetry, therefore, begs for a new way of describing electromagnetic phenomena, and that is how Einstein came up with his special theory of relativity in 1905. How can the speed of light be constant? Let's step back and think about this problem again. As shown in this chapter, there is clearly a conflict between the law of the constant speed of light and the classical velocity addition formula. But this latter formula seems so natural and intuitive, as we saw in the previous chapter. Then, how can the speed of light be the same both from the train and the ground, which are in a non-zero relative motion with respect to each other? How is that possible? Suppose that I ride a horse which runs very fast, say at 100,000 kilometers per second, and shoot a laser gun in the forward direction. I see the laser beam moving forward at speed 300,000 kilometers per second as it should, with respect to me and the horse. The speed of the beam, when viewed from the ground, should then be 400,000 kilometers per second, since that is how it works with the arrows shot from the running horse. And yet, in reality, the speed of the light beam is still 300,000 kilometers per second. How is that possible? As mentioned, Einstein was puzzled by this problem since he was 16 years old. How can the speed of light remain the same, regardless of how fast you are moving? We will call this conundrum Einstein's paradox, Appendix A, in honor of Einstein. Recap of the first 7 chapters. Special relativity is not an easy theory to understand at the intuitive level, despite pervasive misconceptions otherwise. We see time and again why understanding basics is so important in physics. There is so much misinformation out there regarding relativity, broadly speaking, and the special theory of relativity in particular. Einstein dedicates 10 chapters or sections on the foundations of the theory and other relevant basics before he gets to the meat of the theory, the Lorentz-Einstein transformations in Chapter 11. Without this foundation, everything else that follows will seem all puzzling. In the first 7 chapters, we learned what inertial reference frame is and how it is related to a rigid body, matter, and not to space. We learned that time should also be referenced to an inertial reference frame. Overall, we IRFRized classical mechanics. That is, we reformulated Newtonian mechanics so that it would be now understood in view of inertial reference frames. We learned the special principle of relativity. We learned the true meaning of the statement that the speed of light is constant. In general, physical quantities should be defined in such a way that we can measure them in reality. We learned that at the turn of the 20th century, there were apparent conflicts between classical mechanics, e.g., the velocity addition formula, and the law of the constant speed of light, etc. This was how the special theory of relativity was born, as Einstein goes through in the remaining chapters of Part 1. What's next? Now, this is the last chapter in terms of learning the basics of physics and the historical background before we start discussing the special theory of relativity in earnest. For the following 3 chapters, Einstein explores the very concept of time and space to the extent relevant to special relativity. In chapters 8 and 9, he introduces the concept of relativity of simultaneity, and hence, relativity of time, and in chapter 10, he introduces the concept of relativity of distance. Then, chapter 11 includes the equations for the Lorentz-Einstein transformation. A simple derivation of these transformation equations is provided in Appendix 1 of Einstein's book. Chapter 8, the concept of time in physics. Chapter 9, relativity of simultaneity. Chapter 10, relativity of distance in space. Chapter 11, the Lorentz-Einstein transformations. Appendix 1, simple derivation of the Lorentz-Einstein transformation equations.